All right. So last time I was trying to explain machine learning. I was trying to explain that finite state is how we know the behavioral pattern of machines, and finite states are automations that show us what the machines are doing. So they are finite in the sense that we know that language is finite. So if you are training a machine model or machine system and you are throwing a big data at it and then it finds pattern, that is a step in broad AI. Linguistics is a field that is careful about data. So careful in the sense that we don't just throw anything at data. We throw things at data because we know we can get insights from them. So please, if you join, can you just mute yourself because I don't know why we keep having issues with people joining, even repeated participants keep unmuting themselves. I don't know why that. I don't know how we can solve that, but yeah, that has been an issue. I think I just read this. All right, so because machines are learning and what they are learning is language. So because they're learning language, we know that what they are learning is finite form in the infinite sense. So linguistics will go from the finite to the infinite. The machine learning guys will go from the infinite and go to the finite. So finite state machine is what is showing us how finite the data we are learning from is. And I said the fact that machines can actually learn these things shows that they were actually learning the finite form of language. They are streamlining down to the generalization of what linguists would do at the outset. So you have the start state. That is how things begin. I think I explained that the last class. This is where your machine will begin. If you are processing text, you see ES, that's OB or BS, beginning of sentence, something something of sentence, BOS, EOS. So that is very important because machine needs to know when to start obeying instructions. This model is it's a set of algorithms that make prediction. What do I start learning before I can make prediction? Now the transition is showing how it goes around, how it is moving from one to the up to two to three to four. You don't want your machine to jump, for example, from 1 to 7 without a reason, right? Then there is accepting state. So when you have finite state acceptors, that's FSA, it's not finite, it's a subset of finite state machine. A finite state acceptor is saying that if I have a finite state, if I have a finite algorithm, if I have an algorithm designed for the behavioral pattern of my model, if the end of the string coincide to the end where the string where the finite machine ends, then I have an acceptor. So let me quickly just draw a very simple diagram here. I believe you can see my screen. If you have two states, you have off, you have on, and then you go this way, you read A, you go that way, you read B. This is my end state. So what this machine suggests is that anytime I am having a machine, these two signs shows it is the end state. I must end and on. So I must keep this thing on. If I have something like A, B, B, it means I have to go from, if this is my start state, I go from A, I read A, I see B, I read B, I see B again. I am not going anywhere. I'm gonna be here. But this state is a start state. It's not a end state. I don't know whether that makes sense. So that is what your finite state machine is doing. Somebody raised their hand.
I can't see your screen. I've tried to switch screens. I can't see what you're writing.
Well, I don't know. I think, can anybody see my screen?
Yes, if she switches to the first screen
Yeah.
where it reads meeting.
Just switch to the screen at the one I spotlighted. You would see what I'm writing. But I'm no more writing. I stopped writing. All right. So that is the idea behind the finite state acceptors. And you remember that from our finite state machine, we can generate our grammar. What is our grammar? Our grammar is an n-gram, right? The size of the grammatical constraint on our machine. So with this machine, we can extract our rules and we can extract the accepted languages and we can map our machines to any language that can accept any string that can accept our language or our algorithm. You remember that language is a set of strings, right? Okay, so let us go into the formal definition. I try to make that as simple as possible so that this will not cause anything. So a finite state acceptor is a set of tuple in which you have the set of strings, you have the language alphabet as the alphabet you are using, the specific thing you are using to build your language. Like in this case, we have the A and the B or whatever thing we are doing. And we have these states, the off and on state. Then we have a transitioning function that says that your alphabet will go from, if you concatenate your set of strings, so when you concatenate your set of strings into your set of alphabet, you should move to the set of strings. I mean, if you have your grammar, let me see this board. So if you have your grammar, for example, this grammar, you can either give it in positive or negative, right? So I can say, don't end. This is what we used to show end state. This is what we used to show start state in n-gram model. So this is start state, is end state. So if I have this, I can have don't end in B, right? This is my markedness constraint in OT, right? So this one is saying don't end in B, and it will cover for everything because I can have as much A as I can, but I cannot end in A. I can start in A. I have to end in A, but I can't start. I can't start with B. But the B needs to be the let me give you an example. I think this will make it easier. If I have ABBA, I can go from off to on. I can go from on to off. Then I can end at A. So anything that is outside this, that is not ending in A, would give us an error, right? So that is our grammar. So our grammar can be positive or negative. I think I explained that. I can say don't have, and I can say always have. Just as you can say maybe vowel harmony is similar, is a assimilatory or a dissimilatory process in that loose sense of things. All right, then you have your start state, and then you have your set of acceptance state. Yes, Saad.
Yes, please. Can you please come again?
Which one? Which of?
This explanation that you just made now.
Okay, yeah, I'm saying that you can have your set of strings is what you used to and your language is how you go on transitioning function. And you can either create your grammar as a positive thing or as a negative thing. So for example, don't be in a place where you are not accepted. I can also say be in a place that you are only accepted, right? So those are negative or positive way. There are many studies that have shown that learning from positive grammar is different from learning from negative grammar. But I'm not going to go deep into that. So that is just the idea behind finite state. So if you look at this particular slide, can somebody tell me what the math behind this? Can you tell me the grammar? Can you tell me the axioms. Can you tell me? So can you tell me the grammar? If you look at number one, let's do together. We are starting at 0, right? We can have as many A as possible, so we can keep looping. That arc you see there, it's loop. I can keep looping, so I can keep having A and A. Immediately I see a B, I move. I go to 1, I can end, right? Or I can keep having B and B and B. Then if I see another A, I go to the start state. I can keep having a lot of A. Can somebody tell me what the grammar of this language is? What will be the grammar? What language do we accept? Which one do we reject? Notice that we can't end in A, right? But we can have as many A as possible. But we can end in B or C. So we can have A, B, A, A, B, A, A, B, A, A, B, 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 but we can never have A, we can never have A, B, A, right? Because if we have A, B, A, it means that we can't start, we can't end, we would have to be in the start state, instead of the end state. Remember that the 2 circles shows that you are the end state. So what are the languages this finite state machine would accept? It will accept A, B, it will accept A, C, it will accept A, B, A, C, infinite number of A. So I can have A.
I don't think we see what you're writing.
No, I'm not writing yet.
Okay.
I'm just about to write. So we can have A, B, we can have A, C, we can have A, B, we can have A, so we can have A star, B star. This is the size of the grammar, right? So we can have a lot of A, provided we are starting here, right? So this is our start state, this is our end state. So you can keep having A. So far you are at the beginning, you can only end in B. So our grammar can simply say, don't have star A end. So don't end in an A, right? Whatever, I know this is a bit abstract, whatever language you are working on, whatever phenomena you are working on, phonology mostly, that I've applied this to, you can see that you can provide both the constraints, the set of prediction that the codomain that the constraint would apply to, and the kind of system you are dealing with per time without making any prediction outside what you are doing. So for example, if you see a G, you are not making a prediction about a G, yet you are predicting that B and C will be the only end state. See what I'm saying? You know, in optimality theory, for example, they wanted to make predictions beyond what you have. So for example, I want to say something about A, B, C, D, E, F to Z. So I want to say something about A to Z. So they said that if you have a constraint, A outrank B, then this must be true for other successive relations that you have in other languages that is similar to this. But with a finite state machine, you don't even need to make such prediction. All you have to do is to tell us the behavioral pattern of one thing. That thing is always true, no matter what you have. So for example, I know that even if I am not talking about G, and I know G is contained in my alphabet, I am not going to have G at the end of the word. So still, my algorithm is forever faithful. Why? Because I have at the outset predicted that the only thing I want is that B and C must end my string, right? Oops. So B and C must end my string. If I have K, I know that, well, I didn't really make any prediction about K, but I know for one, I cannot start with a K. I will only have to start with A and end with B or C. So in a way, we have not only achieved OT with its constraints, we have achieved what is finitely enough for us to describe a given system. I hope that is very, very important that we catch that. So I don't have to say, imagine you have blue, white, and number of colors, because we don't know these languages, right? Because we might not actually have a given generative candidate, because we will not be generating a candidate, because we are not considering the candidate at a time, doesn't mean that we have not said anything about the candidate. So if I have candidates A to Z, and I have known that this language does not permit only start with A and end in B or C, I don't need any other thing to understand the grammatical system of the language I'm working on per time. That is very important, right? So I will leave the math behind others for us to figure out after we get the slides. You can chat me and I would explain more about that. I need to move. So now, finite state machine, I have explained this. What I'm trying to do here is to give you a set of symbol. I was actually having Yoruba in mind. Yoruba is a Niger Congo language, and what happens in Yoruba is that we use high tone to represent bigness, we use small tone, we use high tone to represent smallness and low tone to represent bigness. So you can have bembe, bembe, bengbe, bengbe, bangba, bangba, I, lolo, like that. And so if I am describing something at a time and I have an alphabet, I have 0 and 1. 0 and 1 is very important at this point. If I have 0, I go to small, so I'm starting at big. So I'm assuming that what I'm having is a reduction, right? So if I'm having 0, I go to small. I must always have something small. I cannot have something big, right? That is what this grammar is saying, because I can only end in small and not uh big. Switch. If I am, I think I will keep saying it. I am not writing on the board. I am on the slide. You can switch to the slide. Okay, so yeah, somebody asked, can I have A, B, B, C? Yes, you can. You can have thousands of C's. You can have thousands of B's. You can have thousands of A. But what the grammar requires is that you must have only A at the beginning and only B and C at the ending. Every other letters from Z to K, W, mention it. Though we didn't mention them in our constraint, we have indirectly make predictions about that. We can't, for example, have Z as the end of the string. So this is what this machine is saying. I must have only something small. I would move. So deterministic finite state acceptors. So of course, I said it's a set of tuples, and you have the finite state, you have the set of symbols you are using. Set of symbols can be phonemes, can be syntactic, whatever, anything you chose. You have the transitioning function, you have the start state, and you have the end state, which is the acceptance state. So I don't need to keep saying this and this again. So non-deterministic finite state machine. So we have two types of finite state machine. We have the deterministic finite state machine, and we have the non-deterministic finite state machine. And you see, it's the same thing. You have the finite state of states, you have the set of symbols, you have the initial state, you have the finite state, final state, then you have the start state, and you have the transitioning function. So if you look at this from wholly everything from Jeff, if I start at 0, see my start state, I can only begin. Who can tell me what I can begin with? I can begin with A, I can begin with B, but I can't begin with J. All right? And I can only end in B. Did anybody catch that? I can only end in B. So what this finite state machine is doing is that if you have a language, you have identified some phenomena, say phonological processes. So, okay, I have a question. The difference, non-deterministic means that you can go to another state without an input. Deterministic means you need an input to move. So if you look at this non-deterministic, you can see that it's an empty. So this epsilon you are seeing here after B is an epsilon, and it's an empty string. I think I mentioned what an empty string is to us. An empty string is just empty, like you are not reading in any input. You don't have to keep track of any memory. So and this grammar says only end in a B. So star end A is wrong. We can't end this machine in A. All right. So this is a classwork. Let us quickly look at this. Does anybody have an idea about what the grammar is? Let's look at 3. Let's look at 3. In 3, what we have is that we can only end in what? Can somebody give me the grammar of this language and what language does it accept? We can start with B. We can start with C. We can start with A. We can end in
1.
Can
We
somebody
can start
mute?
with B and only end with A.
You
can end with B or C.
We can end with B or C. But do you think we can end in A?
Okay, yes, we can end
A
in A.
too.
It has a direct, yes, you can end in A.
Yes, so we can end in A, we can end in B, we can end in C. Can somebody tell me what kind of phonological process this will map to, where you can have, let me write on the board. You can change your screen, please. Apologies if that is not working well. I mean, it's just the way I decided to do it, and I apologize if that is inconvenient. So I can have ask. This is not English. This is abstract, hypothetical. I can have ask. I can have ask, right? I can have kasa, ksa, right? So I can end in K. I can end in S. I can end in A. So whatever you take in, you can also give back. What kind of process could that be? I will leave you to think about that. Let me move. All right. So now I want to quickly talk about function. So you will hear a lot if you take computer science classes and they say you make a function, you make a function, you make a function, and this function and that function. And so what is a function? Even your linear model, it's a function. Looking at a slope and talking about function. So remember that I was explaining something about algebraic structures. And I was saying that algebra is so powerful that if I have an output, it supplies the input that we use to get the output. That is a function too, right? So for example, if my output is impossible, assuming you have an English word impossible, this is English. This is the output I want. This output already predicts the kind of input I would have. For example, I cannot have can here as part of what we give, as part of the inputs to this. Why? Because this output already predicted the kind of input I would get. So if you have a machine algorithm and you are learning from data, it means you are learning the input and the output of the data. You have been given the data. It's algebra, right? So if I have, let me go to math. If I have like 6, for example, this is what I want to get. I know if I'm concatenating, and if I'm adding, if I'm multiplying, if I chose multiplication, if I'm using multiplication, which we do, and addition, if I so whatever you see, I can't remember the operation that I decide to use is depending on the kind of algorithm I am building per time. But I'm gonna stay with addition at the moment. So if I have like 6 outputs, I know that when I choose 4 already predicted the type of thing that will concatenate with it, right? So I cannot have 4 because if I have 4 it's going to give me 8. This is how you set weights in your algorithm. And we'll see that in the last class. I will explain one hot code, how you can embed and how you can multiply vector. I think we'll do vector multiplication here too. So I want you to take a minute and think about it. When we say machine, we are doing machine learning, for example, we are just doing tons of algebraic structure. I know that if I have impossible suggested, if I'm looking at English, that I cannot have I cannot have random words. So it is not true, actually, that these machines are just learning random things. It is true that what they are learning is from big data, which humans doesn't seem like humans learn like that. But it is not true most of the time that all that they are learning is random. It's not random because if they have a set of input and a set of output, they know because by the output, you cannot have some input. The input is predicted because of the output. That is powerful. All right, look at this string. A goes to B in the environment of C. A goes to B in the environment of C. What does that mean? It means that if I have AC, I will write it as what? BC. What kind of process is this? This is a phonological process, right? So whatever process we think about, at a high level, what we are doing is that we are trying to see what the output is. And I am saying that by this output, I mean BC, I know, given this set of alphabet, you know what alphabet means, and this set of strings, and a finite set of strings, actually, I know that my grammar, what my grammar would be, I know what it would look like, I know what it's accepting and what it's rejecting. So you can have a total function, and if total function is everything related to each other, I'm going to give you an example. I'm going to give you Yoruba example. So in Yoruba, we have nasalization. So sorry, I am very used to using phonology examples. So if you're not comfortable with English, I apologize. With phonology, I apologize in advance. So if you have in Yoruba, you're gonna have ninu. This means inside or in. I'll just keep it as in. We're gonna have lowo. This means I'll just keep it as have money. Have money. Then I can have ni, which is have. I can have n, which is spend. I will just write s. I can have la. So what you are saying here is that if you look at this particular set of strings, we can say what we have is we have this alphabet. We have N, we have L, we have A, we have E, and we have U. Is it true? No. What we actually have is that we have in, and we have and we have another R. So you will see that everywhere you have N, the vowel after it is nasal, right? Everywhere you have it. If you look at this place, it's nasal. You cannot have no in Yoruba. You cannot have ne in Yoruba. Why? Because actually, at the underlying level, let's go back to generative phonology. What you have in Ninu is actually li, in, lu. So this guy, because of the mismatch in the process, it needs to spread the nasality. So it's going to spread the nasality here so that linu becomes ninu. But if you see lo, wo, actually it's from ni or wo, that's harmony. This is a nasal vowel. When you delete this nasal vowel, remember that this N only takes its nasality from a nasal vowel. It will turn back to L. So the N becomes L because now this vowel is oral. It's no more nasal. So what I'm saying in essence is that what you need to do is one thing. Don't have what? Nas, oral. So for these multiple processes, it's a total function in the sense that everything relates to each other. Everything is doing one thing. And this is what optimality theory called conspiracy, right? You are trying to, it's as if they are conspiring. Okay, it's a total function. Everything is different. Deletion is happening, assimilation is happening, and that is happening. It's stretched towards even more strings, like Oni Ekpo becomes Elekpo. Everything is hinged on the fact that you cannot have a mismatch in oral and nasal segments because O cannot receive nasality or O is inherently not nasal. You can't have it before a vowel, a consonant that is inherently nasal. And I actually argue in a paper that it is because of ATR harmony. Anyway, what I'm saying in that is that this is a form of total function. Everything relates to each other. If you have a partial function, some things do not follow some things. So everything do not relate. It's just the opposite. Now there's something called monotonicity. Monotonicity says that if you have a constraint in your language, in your finite state machine or in your computing process, monotonicity says you cannot go up and go down, then back up, because that is not linear. So for example, if you look at A in the diagram, the linear function, when it starts, it goes up. In a non-linear function, that's monotonicity is not obeyed. What you have is that it goes up. Look at the B, it goes down and goes back up. So they said this is not true of many processes. For example, if you look at adjective gradation in English, if you have big, you can have bigger, so you can have ER, or biggest, you can have EST, for example. It is not the case that you can have big, biggest, and bigger. So people have explained it as ABA, that's AB. You can have, so if I'm plotting my chart, so if I have like something like this, I can start from here, I can go A, I can go A, B, C, I can go, so if I have another one here, I can't go A, B, let's assume, and then going back to A again. It's not possible. So you can only choose to go A, B, B, A, B, C, but not A, B, A, because that will predict that we are learning, like we are, even though we can reverse our strings, we don't learn like that. You don't learn a language and start going back and forth. Unfortunately, to some extent, in our iteration in the epoch process in your machine learning training medium, they can do this because machine learning is powerful. It's too powerful for what human do. Now we have finite state transducers. So I have talked about finite state acceptor. That's, are you accepting this language or rejecting it? That is a finite state transducer. And what they do is that they transduce from one string to another. Take it as underlying representation and surface representation. So you have some set of strings and they translate. So how in the example I gave about ni, how ni become li is a transduction, right? It's moving from one to the other. For example, in English, let's take the example, let's assume that impossible is derived from in, and possible. So the n has become m at the surface idealization. So it means that what we have in the input is n becoming m at the output representation. And it is the same thing. You have the set of finite states, you have the finite symbol, you have your alphabet. In this case, then you have a finite set of outputs, not just input, right? Then you have your initial state, you have your set of finite states, and then your transitioning function. So if you look at this from Thomas graph, if you look at your machine, you are starting at Y. Just look at the machine. You're starting at Y. What can you do? You can, if you have N, write it as N. If you have P, write it as P. If you have write it as Then if you have R, which is oral vowel, go to empty string. So don't write anything. Don't write anything. So if you are now at this state of NAS, if you have an oral vowel, write it as an oral vowel, then you can end. So the arrow downwards shows end state. It can be this kind of arrow or like the double box. Okay. If I am starting at Y, can somebody tell me what kind of grammar this is doing here? Can somebody tell me what kind of grammar we have here? Look at that state, finite state machine. This FST, and it's still used today in CADI, in different speech model system, speech model, yes. FST is still heavily used. You can see Painini, OpenFST, developed, I think, in New York University, and some other framework now that they're doing LLM. It's still in use. But this is just the specific thing we are doing. So can somebody tell me what this state machine is doing?
To start with Y.
Yes, we can start not Y. If you are having like you're having this A and this tilde on top of it is a nasal vowel. You should start in
Like
You should start
I can just
nasal
what happens is
consonants.
that I can be in a nasal vowel and end. You remember this in the Y, there is this arrow downward showing that it is ending. And you remember this small angle, like this inverted triangles, showing that this, let me see if I can annotate. I'm saying that this guy here is showing end and start state and end state. You remember the arrow that is showing start? And remember the arrow that is showing end. I can start there and end. So I can just have and I will start and I will end. So what kind of grammar am I building?
Is it final state grammar?
Yes, this is finite state machine. It's an FST. This one is showing how we change from input to output. You know that in languages transform. They move from one point to another. What you see at the surface is an effect or is a product of some input, right? Let me see in the chart. You can't see the board. If you change, we are not on the board now, we are on the screen. I am now on the slide screen. So don't let me take your time. I'm gonna move. So here, so let me quickly say what we can have here. We can have a nasal vowel ending the word, right? We can have, if you move from Y, for example, and you have an empty string, so the epsilon there, after the R on this transitioning from Y to NAS, is that you can have that, right? You can have an oral vowel. So when you have that oral vowel, you will write out an oral vowel. Then you can end. What this state is saying is that don't nasalize an oral vowel. So that is what it's saying. You can end in a nasal vowel. You can end in an oral vowel, but don't nasalize an oral vowel. I think I needed to quickly point that out because I wanted to leave it for later before, but I think I need to quickly do that. So this is Igbo. And my intention initially was to give this and people will work it out. So if you look at this data that I doctored, so apologies to, let me know if you have feedback on this data from Igbo native speakers anyway, but this is a paradigm and this is a morphological paradigm. And what I'm trying to just do here is to give machine this time, this particular task that I'm doing. I want machine to take this term, somewhat like gua. This predicts the status of this guy, which is the subject clitics, because of this guy, because of the R, and also predict the status of this guy because of the, so you have a dependency relationship here, right? Everything is dependent on this. What does that say? What this saying is that, what kind of function is this? What kind of function is this? If you are going to give this in function, what kind of function is this where everything is determined on one thing? Just one thing. You remember? That is the total function, right? So what this is saying is that if we abstract away, I'm going to write on the board quickly, real quick. If we abstract away from Igbo, what this Igbo is saying is very simple that we don't have to complicate. It's saying, if I pick, let A and R be retracted and advanced and retracted. So if this is my string, if my set of alphabet, what can I make with this? It's saying if you have A, let me give this as finite state, FST actually. Let's assume we have A, we have R. If I have anything, so here, I'm starting here. If I have, I don't want to give real alphabet. If I have C, and I'm at this state, I should write it at C. No, let me keep it here. If I have C, I should keep it at C. If I have D, let me leave. and come here. If I am here and I see E, write it as actually advanced retracted. What I'm trying to do is to show that when I have anything ATR, output ATR, immediately I see if I am in, actually this is even simpler. Wait. This is even simpler. I know I'm running out of time. So if you have A, I want to keep having A. I want to be, if I have C, I want to keep it, I want to be in C. If I have B, if I have R, I want to keep being in R. So let's say I have D, I want to be in D. Take D as retracted, and I hope this is clear enough anyway. Or is it upside down? I don't know. If you
Yes,
take this
it's
as
upside down.
it's upside down, right?
Yes.
Is it okay now?
Yeah, it's okay.
Okay. So if I have anything advanced, I want to keep it at advanced. Anything retracted, I want to keep it retracted. But then the question is, how do we now put these guys together? How do we put them together? Can somebody know? Can somebody explain how? Can somebody think of how this might relate to each other? So, for example, they don't relate, but we can relate them by empty strings. They don't relate in the sense that you don't want a mismatch in tongue groups because Igbo does not permit that, right? So if you have a stem verb, you have a stem verb. So if you have like a stem, and you can see that its stem is ATR, maintain ATR. If I have a stem that is RTR, maintain RTR. This is just showing that there is not overlap. There is no overlap in this set, right? So if I have a set of ATR vowel and a set of retracted vowel, everything must be kept away from each other, except like I have a consonant. I have a consonant and I want to loop the consonant. So even if I have a consonant, say K, K would always come out as K, and I want K not to be affected by this tongue root position. So there are a lot of tricks you can do to relate them. You can use empty strings, you can do a lot of concatenation, you can extend the tape, you can multiply the finite state machine, which is way, way complex than what I am trying to do here, but I'm trying to keep it simple. So you can't draw this FST. You can't draw this FST and relate them. But it's powerful in the sense that I need just one state. If I am in that state, everything is taken care of, which is interesting, right? So I need to only figure out the specific state that I am. That is what a decision tree would do for you. Is it Ostia? There was an algorithm created by, I think Jufrasky was part of the author. It's Ostia, and in Ostia, it's the same thing. You look ahead and you make your decision. We should talk hopefully about that in the last class. Now, so I want to quickly talk about vector. So can somebody let me know what the time is? So all right, I will just talk about vector and we'll call it a day. So the vector, it's just like a mathematical object that is explaining the magnitude or the size of a given phenomenon. So you have the rows and you have the columns. And this vector space is the structure of your vector. So how many numbers do you have? How many rows do you have? Now, we need to learn what this vector is doing. So if you have 1, 0, 0, 1, and you have 1, 0, then you take the dot product, you multiply this by this, you multiply this by this, then you add it together. So for example, if you have this, you have 1, right? You have 0, and then you have plus 0, 0, right? What do you have? You have 1. So how do we get this vector? I will take it again. You multiply this guy by these guys, and you add the result together. So how does this relate to finite state machine? Actually, we can convert our finite state machine to vector. So I will give you an example of how we can do that, and I will leave you to go over the Swahili thing. Okay, I think I can actually use the Swahili example to illustrate. So our finite state machine as machine learning algorithm is simply conversion of our finite state into a vector. Let us look at the simple machine. I will call it 1, 2. So A, B, very similar to what we have in Swahili, right? So anywhere we see, if you have a set of strings, so we have A, B, A, I complete this a little bit. So if I have C, so I can have something like cat. I can have something like Kaba. If I have this, what does this say? It's saying that first, we have 2 states. That's powerful. If I have this set of strings, I would have, if I have C, let me start with the C. I would get the vector of each of these inputs, and I will multiply them to get their output. So for example, if I have C, I know it is possible to start with C. Where it is possible, I would put 1. Where it is not possible, I put 0. Okay. Where it is possible, I'm converting this to binary. When it is possible, I put 1. When it is not possible, I put 0. If I have a C, I can start with a C.
I can start with a C.
Oh my. Can you mute yourself, Abdul Fattah? Something. Okay. I can start with a C. I can end with a T, right? That is 1. If I have this, then I have what this simply means is that I am only extending by 1, and I can keep it like this. There is no issues, since I can have these strings and I can have that string. Now, if I have kaba, so if I have something like let me see how I can simplify this. If I have something like ba ta, so if I have a B, so this is accepted, right? This is 111. This is finite state acceptor, not FST. No FST yet. I would go over the FST later. When I have CABA, I would have 111, right? When I have BATA, I would have 0, and I will have 111, right? Any 0, no matter how the number, I can have 0001, 000011, as in this. It is outright rejection. So for a finite state machine, we can convert it to metric space, and in terms of binary, we can keep it simple in binary so that we can achieve a lot of things with it. And what this finite state acceptor is doing is that it's showing us the vector space. It's showing us that we have 3 things, right? So we have like 3 alphabet, and it's telling us that we are in 3 space to make our decision, and any of these that is 40 is a rejection. So in machine learning, what we do is we do vector multiplication, but I'm trying to start with a vector conversion of an acceptor. We will do FST. I will start with FST in the next class. So what our FST is doing, our FSA machine is doing, is that it's telling us that the size of our hypothesis space, our vector space, is 3. The size of the alphabet we are considering per 1 is 3, and any fault in either of these alphabet, it's a rejection of string. So this is an example of how we can embed our alphabet, our letters, our grammar. Remember what grammar means, our set of strings and everything like that. So in the next class, I would start by converting an FST into a matrix vector like this, so that we can do the multiplication and see. That's the step I put here. But I need to start with an FSA. So I would leave you to go over the Swahili assignment, the Swahili data, come up with the finite state machine, convert it to a vector acceptance space, and ask your questions in next class. So I would be rounding off here so that the next person can so that we can have space for question. Let me see if I have other things here. So yeah, I do have another data there. So do we have questions? So what we've done is that we've converted a finite state machine to a vector. I will convert an FST to a vector in our next class. We will do the multiplication to predict the kind of output that we have. And I will show you that that is actually what machines are doing, I mean, in the internal level, at the internal level. Do we have questions? No, the material has not been shared. I would share it later. I guess this was clear enough, right?
Not really.
Okay.
But I don't know when the recording will be available so that we can at least watch and grab some other stuff from the video.
Yeah. Yeah, it should be available by tomorrow. I'm juggling things, so I would be able to finish up the uploading by downloading and everything by tomorrow evening or tomorrow by the end of tomorrow's class. Everything should be ready on YouTube.
All right, thank you.
Yeah, so the finite state acceptor is what we covered. Next class, I will go quickly over finite state. All right, so I will leave the video to, I believe we don't have questions then. So I can stop recording, right?